In this lecture, I'm going to talk about another method for finding the volume of a solid using integration. It's called the shell method, also known as the method of cylindrical shells. The idea is, well, here's an example of one shell, and then I'll kind of give you the big idea of about how the shell method works. So if we have this rectangular piece here, and we call this length here W, and this length here H, and then the distance from the middle of the rectangle to, in this case, the x-axis, but whatever the axis of revolution is. We want to let P is that distance from the axis of revolution to the middle of this rectangle. Then what we're going to do is we're going to rotate. You can think about just taking this, and we're just going to rotate it around the x-axis, and it's going to sweep out this shell. It's basically a cylindrical shell. It's a shell in the sense that it's hollow, and the idea is that we would take, for a given solid, we would put in a shell kind of around the widest part, and then another one, and we'd have these concentric shells getting smaller and smaller, basically filling this thing up. So if we were to find the volume of one of the shells, and then find the volume of the next shell, and the next shell, and the next shell, and then add up the volume of all the shells, that would give us the volume of the solid. So that's the big idea behind this idea of the shell method. So in order to do that, though, we need to start with the volume of one shell. So we're talking about this solid piece here. So if we take the outer cylinder, basically if we had a solid cylinder here, then that would be the outer cylinder. And then the inner cylinder is the part that's removed. So if we take the volume of the outer cylinder and we subtract the volume of the inner cylinder, then that should give us the volume of this shell, of what's left. So let's think about how to find the volume of the outer cylinder. So what we basically, for a cylinder in general, if I take the radius of the cylinder, so in this case, and I guess maybe it might help to use another color here. So the outer cylinder, the radius, is this distance here, right? From the axis all the way to the outside. And so if we come back over here, what we're doing is we're taking the top of this, right? But if P is the distance from the axis of revolution to the middle, then this distance is going to be P plus W over 2, because it's half of this width W added on to P to get to the outside. And then if we were to find the radius for the inner cylinder, so going this way, that's going to be P minus W over 2, because again, we're at P, we're coming down here, we know that distance, so we can kind of think this is the green distance over here. This is the red distance. So again, this is P plus W over 2. This is going to be P minus W over 2. And again, that's just, if we're looking just at the face of this thing, then what that's giving us is the radius. And we know that the area of the face, so the area is going to be pi r squared in both cases, right? Pi r squared, and then we multiply by basically the height of our cylinder, which is h. So it's going to be pi r squared h here and pi r squared h here. The difference is that we have a different radius, right? This is this equals the outer radius, where this equals the inner radius. So the r's are different. So let's go ahead and plug those in and see what that gives us. So this is going to be pi times, and we said the outer radius is P plus W over 2 squared times h, and we're going to subtract from that pi times P minus W over 2 squared times h. All right, well, there's some algebra involved here. I'll do one step, but I don't want to bore you with too much of this because it's really just algebra. This is going to give us P squared plus PW plus W squared over 4. That's just expanding this times H minus, and this is going to look awfully similar, except I'm going to have a minus PW instead of a plus. But the first and last terms are exactly the same because when we square them, sorry, this is a P squared. When we square them, it doesn't matter that it was negative. And then we have the H. So if we distribute the pi and the H to all these terms and we combine, well, yeah, let's combine our this. If we distribute here, what we're going to end up with is what? Pi P squared plus, whoops, pi P squared, well, put the H out here, and then pi P W H plus pi W squared over 4H, and then minus pi P squared H, and then this is going to be plus, distributing that negative, pi P W H, and then finally minus pi W squared over 4H. Alright, well, I guess I am going to go through all the gory details here of the algebra. But the thing is that this cleans up nicely because this and this cancel, this and this cancel, and I'm just left with pi PWH plus pi PWH, or 2 pi PWH. Alright. Okay, so that gives us the volume of one cylinder. Alright, and then we could do the next cylinder inside of that, and the next cylinder inside of that, and then ultimately we let the number of cylinders, of cylindrical shells, go to infinity, and that leads to an integral. So let's take a look at what that integral would look like based on the volume of one shell. Okay, so just to kind of keep this, we have this 2 pi PW, and we can look at this, whoops, try to get centered here, well, close enough. Okay, so we have two cases here. One is if we're revolving around the x-axis here, right? So we draw in our little rectangle as we did in the previous, and we're going to, one thing to notice is that the rectangle is always going to be parallel to the axis of revolution. So here we're revolving around the x-axis. Really, this is going to be applicable to any time we're revolving around a horizontal axis. And then in this case, we're looking at revolving around the y-axis or any horizontal. So maybe that there could be an axis out here and we're going to revolve around that, but we set this up the same way. So again, I would suggest whatever your area is that you're revolving, I would draw in your little rectangle and label these. So the P is now going to be P of y in the sense that this distance from the x-axis to the middle of our rectangle is going to be a vertical distance, so it's going to be in terms of y. And then here, this will frequently just be our function, whatever our function value is. And then notice that previously we had w, but now we're just going to call that delta y. That's the change in y, right? How wide this is in terms of y. And we're integrating, well, our region starts at C and it goes up to D. And we're revolving, so C and D are y values. So the way this works out in terms of this formula here is that we are going to end up with our volume will be 2 pi, and we're going to integrate because we know that if we take the sum of all these and let the number of them go to infinity, that results in an integral. And we're going to integrate from C to D. So this integral is going to be with respect to y, and we're going to have P of y times H of y, and then as we let that limit go to infinity, the number of cylindrical shells goes to infinity, our delta y becomes a dy. So this is the formula in the case where we're revolving around the x-axis or horizontal axis. Here then, if we're revolving around the y-axis or some vertical axis, very similar. Again, P of x is the distance from our axis of revolution to the middle of the rectangle. This height will be again, generally our function value, but we'll see some examples of that. And then the width is delta x. As it goes to infinity, we end up with something very similar. Whoops, we're going to start with 2 pi out here. And then we're going from a to b because we're integrating with respect to x. So this is going to be P of x, H of x, dx. So this is how our formulas end up. And again, I think it's this is the key, is to setting it up correctly, thinking about if you're revolving around the x or y axis or horizontal or vertical axis, setting this up and labeling it. So let's just look at a couple of examples, because I think that will help to make sense of these formulas. Alright, so I'll try to leave the formulas in the screen as much. Well, how about just the formulas? Alright, so here's what we've got for the first example. So we want to find the volume of the solid of revolution formed by revolving this area between x minus x cubed and the x-axis. So it's this area here, and this is from 0 to 1 on the x-axis, and we're revolving around the y-axis. All right. So since we're revolving around the y-axis, let's just put in a sample rectangle here that's vertical. It's oriented vertically to be parallel with the y-axis. So again, we need to figure out, here's the distance from the y-axis to the middle of this. That's p of x, and that's just going to be whatever that x value is. So p of x equals x. So if we're revolving around the y-axis, then it's just generally going to be p of x will just be x, because it's the distance from the y-axis to the middle of the rectangle. And then the height of that rectangle, we know the y value here is just given by the function, so that's going to be x minus x cubed. And of course, this is delta x that goes to dx when we write it as an integral. So to set up this integral, the volume, we always have that 2 pi, and we're integrating, and we're going to integrate this from 0 to 1, because that's where our region is, from 0 to 1, and it's going to be p of x times, this is our h of x, p of x, h of x, so it's just going to be x times x minus x cubed dx. Alright, now I won't bore you with the details of the integration, because we just distribute to x. This is the straightforward power rule antiderivative, and if we plug in the values and multiply by 2 pi, we will get 4 pi over 15. So you might work through the details if you're not sure about that, but this is what you should end up with if you do that correctly. Okay, let's look at another example, and this time we're going to revolve around the x-axis. So again, notice what we did just real quick. This is our p of x and our h of x. This is the formula we used because we were revolving around the y-axis. Now we're going to be revolving around the x-axis, so we're looking at setting up something like this, right? We know that our rectangle is going to be oriented. Whoops, get that over there. It's going to be oriented horizontally. So the area that we're looking at is the area between x equals this curve right here is e to the negative y squared and the y-axis. So now we're looking at this as being the area, and we're going to revolve it around the x-axis. So let's draw in our rectangle. So here's our rectangle. We know that the width is going to be delta y. All right, and then we're looking at this height, this distance from the x-axis up to the middle, and again, we're just going to call that y. That's p of y, and we'll just call that y, because the y value right in the middle of that is going to give us the distance from the x-axis up to the middle. And then here, the width of this, again, that's our h of y, and that's just going to be, so our function, e to the negative y squared. Okay, so again, using this formula, we found p of y, we found h of y, and we're going to be integrating from c to d, so in this case from 0 to 1. So our volume is 2 pi integrating 0 to 1, p of y, which is y, times h of y, which is e to the negative y squared dy. Okay, so just think for a moment how we might approach this integral. You might even just pause the video at this point and go ahead and try this integral. Okay, so either you decided not to, or you have now pressed play again. Let's go through how to find this integral. Well, notice that y is a multiple of the derivative, a scalar multiple of the derivative negative y squared, right? So if I let u equal negative y squared, then du equals negative 2y dy, and I have a y dy to substitute for here. So if I divide out a negative 1/2, then negative 1/2 du equals y dy. So I end up with an integral that looks like this: 2 pi 0 to 1 e to the u du. Now I could change the limits of integration, or I could wait till the end. Either way is fine. I'm just going to leave them, and I'll go back to y after I integrate. So technically my limits are in terms of y, but I'm doing an integral in terms of u. But I'll go back to y, so that's what at y it doesn't matter. All right, well, integral of e to the u du is just e to the u. So this is going to give me 2 pi e to the u, and again these are in terms of y, so I need to go back to y. So 2 pi, and this is e to the negative y squared, 0 to 1. If I plug those, oh, and whoops, this has to go out here, right? I got that negative 1/2. So let me just bring that along. Negative 1/2, negative 1/2. Right, so negative 1/2 times 2 pi, that's going to just give me negative pi, and then I'm going to have e to the negative 1 squared, which is e to the negative 1, minus e to the 0, or negative pi 1 over e minus 1. Finally, if I just want to distribute this negative, I would have pi times 1 minus 1 over e. All right, so the difference between this example and the last, here we're revolving around the x-axis, so our integral turns out to be in terms of y. All right, for the final example, I'm going to just do one where we're not revolving around the y or the x-axis. How do we determine h and p in that particular case? So here we're going to find the volume of the solid formed by revolving the region bounded by, so this is y equals x cubed plus x plus 1. This is y equals 1, and here's x equals 1. So we're looking at that region, and we're going to revolve it around x equals 2. So this is going to be a vertical axis of revolution. So vertical axis, or the y-axis, right? So it's going to look something like this, but p of x and h of x will be determined a little bit differently in this particular case, because our region doesn't go down to the x-axis, and we're not revolving around the y-axis. So we'll look at how to do that. All right, so let's first put in, again, a representative rectangle here, and as always, the width of that will be delta x. Now, let's think about how we can find, let's first start with h of x. So the height of that rectangle. Well, the top of it is going to be, the top of that will just be this y value right here. So that's going to be x cubed plus x plus 1. But it doesn't go all the way down to the x-axis. It stops here. So it's this value minus the bottom value, which anywhere along the interval is going to be 1. So I'm going to just subtract 1. So that is my h of x. And then for my p of x, we're looking at this distance right here. Right? Well, this is the larger x value, this is the smaller x value. If I was revolving around the y-axis, I would just call this x, right? It's the distance from the y-axis. Here, though, I'm looking at this distance from 2 over to x. So that's exactly what we're going to call it. We're going to call it 2 minus x, because our rectangles will move around. You know, depending on where they are, it'll be that particular x value. But we're always revolving around 2, so that's constant. All right, so let's put this all together then. We are going to end up with our volume equals 2 pi, and we're integrating. So here we're integrating along the x-axis, so we're going to go from 0 to 1. And this is going to be 2 minus x. That's our, I didn't write that, but that's our p of x, times h of x. And notice if I subtract off the 1, I'm just left with x cubed plus x. So x cubed plus x dx. All right, and again, we can distribute that out, and plug in the values. I'm not going to go through all the details, but that will give us 29 pi over 15. So again, you can verify that for yourself. This isn't a difficult, I only wanted to go through the one that required a little bit more in terms of substitution, but this is straightforward. Expand and just use the power rule to find the antiderivative, plug in 0 and 1. Alright, so that is the shell method. We looked at 3 different examples revolving around the x-axis, the y-axis, and some other axis that's neither the x nor the y-axis.